So what I want to talk about today really is just one example, a naturally occurring example in mathematics, in fact in complex dynamics, in which one sees very naturally an interesting subgroup of a big mapping class group, in particular the plane minus a counter set. So I want to start by talking about just polynomials. So if I have a polynomial, let's say f of degree d, well, it doesn't have to be monic, but we can always conjugate this so that the linear term, so by a linear change of variables, so that the sum of the roots is 0, so we can put it like that, so this, the linear term is 0. Obviously, it's going to be different coefficients from before. I should have given them different names, but anyway. And we say that this is being put in Butcher form. If you have a polynomial, you can associate to the polynomial the collection of roots. If I have a degree d monic polynomial, there are d roots. So polynomial is sort of degree d is given to you basically by giving you d complex numbers, but not in order, right? They're just d complex numbers, and some of them might be the same and some of them might be different. And so there's something called the discriminant locus. So this is a subset of, well, so here I'm going to look at c to the d minus 1. So I think of here as the a2 up through ad are the coordinates. And a point is in this discriminant locus if this polynomial has a multiple root. Okay, so a point, so this discriminant locus sort of is exactly the space of polynomials of degree d in this sort of normalized form with a multiple root. And in particular, c d minus 1 minus delta, this is exactly corresponds to, well, okay, so this is a, so I'll say, so the sets of d unordered, distinct, complex numbers, and I've normalized it so that the first coefficient is 0. So these are d unordered distinct complex numbers that sum to 0. So I could just as well think of the subspace of CD, the set of unordered distinct complex numbers without imposing the condition that they sum to 0. But if I have a set of complex numbers, I have a set of d complex numbers, well, I can just translate them around so that they sum to 0. So the space these two spaces are homotopy equivalent. So either imposing the condition that the roots sum to 0 or not imposing that condition gives you at least homotopy equivalent spaces. It's a little bit easier to work here because it's slightly smaller dimension. All right? In particular, if we had, so for example, if you have a cubic polynomial, and now suddenly my variable has become x rather than z, let me make it z, cubic polynomial in this form, then the discriminant is the subset of C2 for which this relationship here holds. So minus 4p cubed minus 27q squared equals 0. So this is a subset here of C2. We think of C2 as the plane, well, the complex plane, but then this thing here defines, well, the coefficients aren't that important. We can think of it as, you know, p cubed plus q squared equals 0. It's kind of a cusp singularity. So this is the discriminant. So this is sitting in C2. So the complement of this, so C2 minus the discriminant, basically it deformation retracts onto, we could take a small sphere, so this is S3, the unit, real unit sphere in two-dimensional complex space, and it intersects this discriminant in a knot. So S3 intersect this discriminant is a knot, and S3 minus this knot is homotopy equivalent to this space C2 minus delta, okay? So what is this knot? This knot is actually, turns out to be the right-handed trefoil. So this is just an example here. So S3 minus the right-handed trefoil up to homotopy equivalence is a nice space parameterizing polynomials of degree 3, monic polynomials in degree 3 whose roots sum to 0, which don't have multiple roots, which have distinct roots. Okay, so this is a very nice space. So these spaces are very nice. They have some very nice properties. So first of all, well, I know first of all, these are k pi 1s, which means that, well, their fundamental group is whatever it is, but all the higher homotopy groups vanish. They have the homotopy type of a complex CW complex of half the dimension. So in other words, they have the homotopy type of a complex of real dimension d minus 1. It's not obvious, but this turns out to be true. And maybe more importantly, for our purposes, the fundamental groups are mapping class groups. Well, it depends how you sort of think about them. In particular, pi 1 of this space, CD minus 1 minus delta, either is by definition or is isomorphic to the braid group on D strands. And this is the mapping class group of the disk minus D points fixed on the boundary of the disk. So you look at homeomorphisms of the disk permuting D points fixed on the boundary, and you look at pi 0 of that space, and that's by definition the braid group, or the braid group on D strands, and that turns out to be isomorphic to this space. And it's sort of not surprising, as a polynomial gives you these D points, these D distinct points. If you move around in the space of polynomials, if you go around a loop, these D points move around in an interesting way and they come back to themselves and they give you a braid. All right? So what I want to talk about now is sort of a, not a generalization exactly, but an analogy of this picture to some natural space that turns up in complex dynamics. One's going to get a space. This space is going to have some very similar properties. It's going to be a k pi 1. It's going to have the homotopy type of a complex of a half its dimension. And its fundamental group is going to be, in a natural way, a mapping class group. But it's not going to be a mapping class group of a surface of finite type. It's going to be a subgroup of the mapping class group of the plane minus a Cantor set. And one thing that sort of almost goes without saying in this particular context, this space delta, this discriminant, it's defined by some polynomial equations, so it's a complex variety, and its complement is therefore also, well, a variety. It's a quasi-projective variety. So these spaces are quasi-projective varieties. It's going to turn out that the spaces that I now want to talk about arising in complex dynamics, they have a description in terms of algebraic geometry. They can be described in terms of quasi-projective varieties. So you're going to get a space, the fundamental group is going to be infinitely presented. It can't be, on the face of it, pi 1 of a quasi-projective variety, but there's going to be description in terms of algebraic geometry, which is sort of analogous to this picture here. And in fact, the spaces that I want to talk about are going to turn out in a natural way to be a kind of, just sort of a refinement of the picture for braid groups. So if you just care about braid groups, you might still be interested in what I'm going to talk about today. So I want to talk about the shift locus. So I'm going to talk about, so this is a subset of, so C d minus 1, which here I'm thinking of the set of polynomials of degree d up to conjugacy, or equivalently, in this Butcher form, right? So just normalize my polynomials so that they're monic and the roots sum to 0. Right? If you have a degree d polynomial, you can always put it in that form. It's the subset with the following property, for which all the critical points are in the attracting basin of infinity. Under what? Under iteration of the polynomial. So i.e., we have this polynomial, z goes to z to the d plus a2 z to the d minus 2 plus a3 z to the d minus 3 plus a sub d. The critical points of f, it's just, I mean, the roots of f prime. So you can write them down. They're algebraic, well, okay, they satisfy algebraic relations that are expressed in terms of the AJ. And we want them to be all in the attracting basin of infinity. This means for all critical points C, we have C, we apply f to it, we get f of C, f. So this notation f circle 2 or 3 just means apply f twice or 3 times or whatever. This sequence converges to infinity. So it's a polynomial of degree d. So in particular, if you have a complex number whose absolute value is big enough, then f of it is going to be pretty close to that number to the power of d. So once you're close enough to infinity, then you keep applying f, well then you head off towards infinity very quickly. So f, infinity is in the language of complex dynamics, is a super attracting point. So points that are sufficiently close to infinity just head off towards infinity in a very orderly way. The dynamics is very simple. Away from infinity, we don't know what happens, but we want the critical points all to be in the basin of attraction of infinity. So this turns out to be equivalent. So F in the shift locus, and I should give this a name, so script S sub D. So this is the shift locus in degree D. F in the shift locus turns out to be equivalent to two things. First of all, that the Julia set of F, I'll say what that is in a second, is a counter set, and the action of F on its Julia set is uniformly expanding. I mean, in the appropriate sort of metric. So this is sort of equivalent to saying that the Julia set is a counter set and none of the critical points maps into the Julia set or is contained in the Julia set. So what's the Julia set? There's several different definitions of it. Basically, it's the set with the property, it's the complement of the set on which F and its iterates are a normal family. So away from the Julia set, F and all of its iterates do something very uninteresting. Things just sort of, the dynamics is somehow extremely boring. The Julia set is the set where maybe there's interesting dynamics. It's the closure of the set of repelling periodic orbits. So all but finitely many periodic orbits are repelling. So there's the finitely many attracting or indifferent ones, and they have maybe their own interesting dynamics. But all the other periodic orbits are repelling, and they're dense. Their closure of them is this nice, interesting set called the Julia set. The dynamics tends to be very kind of chaotic there. It's the analog, if you think in the world of, like, say, Kleinian groups, that's the analog of the limit set of a Kleinian group. If you think of like a iterated function system, it's the analog of the attractor of an iterated function system, or maybe you'd think of the inverse of the system or something. So F is uniformly expanding on this Julia set. In particular, there's no critical points there. So in particular, you can look at the inverse of F near this Julia set, and it has D kind of pre-images locally. Each point has D pre-images locally. So there's sort of D inverse branches of F near the counter set. And the way in which the inverse branches of F act near this counter set is exactly that they just take the Julia set, which is a counter set. The Julia set is made of D pieces, and the inverse branches just take the Julia set and they shrink it down to one of these pieces. So another way of saying that is that the way in which F acts on its counter set, the way in which F acts on its Julia set is just sort of conjugate to the standard shift on a D-letter alphabet. Just takes the Julia set, expands it by a factor of D, and wraps it around itself D times. Okay. So the action of F on this Julia set is just like the shift, is the shift on a D-letter alphabet. Hence the shift locus. All right, so the dynamics is extremely simple on the Julia set, and the fact that it's uniformly expanding says that the dynamics of F is structurally stable near this Julia set, near this counter set. So if I move F around a little bit in the shift locus, well, the counter set moves around in a way in which I can kind of track the motion of the points by the dynamics of F nearby. In particular, the way in which this Julia set moves, when I move F around in the shift locus, it extends to a family of homeomorphisms of the plane, uniquely up to isotopy of the counter set. In other words, if I have a one-parameter family of polynomials in the shift locus, well, the counter sets move around in some interesting way in the plane, and if I have a loop in the shift locus, I get a one-parameter family of motions of the Cantor set in the plane, and it gives me a well-defined element of the mapping class group of the plane minus a Cantor set. So there's a kind of a monodromy map, pi1 of the shift locus maps to the mapping class group of the plane minus a Cantor set. Well, all right. So the way in which one analyzes the shift locus, so maybe an example. If d equals 2, so the shift locus, so this is a subset of C1, which is to say C. So these are polynomials of the form z goes to z squared plus c, for which the critical point, and the critical point is just i.e. 0, is in the basin of attraction of infinity. So this is equivalently, i.e. 0 goes to c squared plus c, goes to etc., heads off to infinity. Well, so this is exactly what it means for the parameter little c not to be in the Mandelbrot set. So this thing here is exactly equal to the complement of the Mandelbrot set, or maybe you call it the Brooks-Metelsky set, but anyway, the Mandelbrot set, if you know what that is. So knowing that something about the topology of the shift locus tells you something about the topology of the Mandelbrot set. So the shift locus in degree 1 turns out to be homeomorphic, actually conformally equivalent to a punctured disk. The puncture somehow corresponds to the point at infinity. The Mandelbrot set is a bounded set, so the complement of this punctured disk in C is something which has the topology, or at least the homology, of a disk. In particular, it's connected. And H1 is 0, and because it's planar, that means it's simply connected. So this implies that the Mandelbrot set is connected. So if you want to know something about the topology of the Mandelbrot set, you can prove it by proving something about the topology of the shift locus in dimension 1. Or shift locus in degree 2. Sorry, this is, I don't know why I wrote a 1 here. 2, which is sort of, sitting in C2 minus 1. All right, so in fact, this is the proof, the Doherty-Hubbard proof that the Mandelbrot set is connected is exactly, comes down to proving that S2 is conformally equivalent to a punctured disk. But anyway, you might, in higher degree, want to know about the analog of the Mandelbrot set in higher degree, and maybe the topology of these spaces becomes very interesting and very complicated, and understanding the topology directly might be hard, but you can say something about it, for instance, its homology or whatever, by understanding the topology of its complement, and so that's one of the motivations for studying the shift locus. So I might as well say, since I wrote it up there, so the shift locus has some nice properties, and so this shift locus turns out to be, it's a K pi 1. It has the homotopy type. Of complex of real dimension d minus 1. So this is, part of this is joint work with Mary Hay and Juliette Bavard. And, well, maybe I should mention Sarah Kirk and Alden Walker. We had a project which sort of somehow fell apart, but this particular piece of it I think was really Mary and Juliette focused on. the natural map from pi1 of the shift locus to this mapping class group, what I was calling gamma, mapping class group of the plane minus a counter set, is injective. Finally, this thing I was saying about algebraic geometry, I'll say there's a way of understanding can be understood. There's a very vague statement in terms of certain quasi-projective varieties. Well, something which is a kind of an infinite increasing union of quasi-projective varieties. So let me say a little bit about where this comes from. So if you want to understand a polynomial in the shift locus, the way to do it is, so you've put it in this Böttcher form, z goes to z to the d plus a sub 2 z to the d minus 2. Oh, sorry, is that me? And so on and so forth. Putting it in that form means that it osculates the map z goes to z to the d at infinity to second order. In particular, that's enough to show that there's a kind of conjugacy. You can sort of formally write it expanded as a power series near infinity and compare it with a map z goes to z to the d near infinity, and you can find a nice conjugacy, at least formally, between these maps at infinity. And basically, I think this is Hensel's lemma, or Newton's method, really. And by kind of thinking about convergence of this power series, you can get a conjugacy between the map f and the map z goes to z to the d near infinity. So I'll sort of say this is the way to understand some element of the shift locus. So here is the map f, and here's the map z goes to z to the d, and there's a conjugacy. We can find an open neighborhood of infinity here, an open neighborhood of infinity here, and a nice holomorphic isomorphism, so that the action of f here is conjugate to the action of z goes to z to the d here. Well, so we have a conjugacy defined in the neighborhood of a point infinity. It's natural to say these are both complex analytic dynamical systems. We can extend this conjugacy. I mean, phi is just a nice complex analytic map. We can just extend it by analytic continuation until what? Until we run into trouble. So let's do that and see what kind of trouble we run into. Well, we're going to have to run into some trouble at some point, because certainly globally these maps are definitely not conjugate. And the reason is the Julius set of z goes to z to the d is the unit circle. In particular, the filled Julius set, so just the sort of the subset shielded from infinity by the Julius set here, is the unit disk. And so under the iterate z goes to z to the d, the unit disk just maps to itself. Whereas over here, we have some Julius set, which is a Cantor set. And on the complement of that Cantor set, an open dense subset of the Riemann sphere, f just maps all of those points off to infinity. So there certainly can't be any global conjugacy, or even a very nice global kind of mapped semi-conjugacy between them. It's very incomparable kind of dynamics globally. So something has to go wrong. And so what goes wrong is that the map z goes to z to the d, well, it has a critical point at infinity, and it also has a critical point at 0. But it has no critical points in the basin of attraction of infinity, apart from infinity itself. Whereas this guy here, by hypothesis, has a bunch of critical points. So these are the critical points of f. It has, well, d minus 1 of them with multiplicity. And these guys definitely are in the basin of attraction of infinity. And so this is some point where the dynamics here is just definitely different from the dynamics here. So when we try to extend this conjugacy phi, we're going to run into trouble at the critical points and their preimages. Okay, so, but in the neighborhood of infinity, we're okay. And so actually we can kind of look at, there's a nice foliation here. Actually, the foliation is kind of globally defined here. There's a foliation of the sort of northern hemisphere here by lines of constant longitude. Is this what they're called? Constant argument. Complex numbers with constant argument. And that conjugacy, we pull it back, we get a kind of a similar foliation here, at least in some little neighborhood. And we can extend this down until it comes to the critical points. And when it comes to the critical points, this foliation becomes singular. So maybe there was some other guy that came around the back here and did something and landed something like this. So I think this is the picture here. We have some kind of singularity in which we have these, well, I don't know, whatever, things coming around like that. Something which was a straight line over here, the analog of it has branch points because the behavior is kind of branched by the existence of these critical points. We could draw another foliation here if we really wanted to pin things down. We have a foliation not just by lines of constant argument, but lines by, well, circles of constant absolute value. So we can kind of get this sort of foliation here, and we can pull that back, and again, we get a sort of similar thing here, and something funny happens when we get to these critical points. Basically, you have maybe a circle passes through one of these things here, and it breaks open into a bunch of smaller circles. So we get kind of a singular foliation here, which is sort of the pullback of this foliation here under the map phi, analytically extended as much as we can extend it. So the correct picture, if you like, is that we can extend the map phi globally to a conjugacy between, well, f acting on the complement of its Julia set and, well, z goes to z to the d acting on, it's not quite c minus the unit disk, it's this thing, but we have to sort of take a branched cover of this. Or rather cut and paste. So we take this and we do a certain kind of cut and paste on it where at kind of the points corresponding to the critical points in their preimages. Cut and paste at places corresponding to the critical points and their preimages. Okay, so topologically, we imagine we just have z goes to z to the d. We have this nice sort of pair of foliations. I'm just redrawing the blue and red foliations here. I guess maybe I can just redraw them in blue and red. And that's okay for a while. Infinity's here, just have taken it out of the picture. And that's okay, except at some point, you're going to get two different points here, which want to come from the same point over here, the same critical point over here. Okay? So you're going to have maybe two different points here that they both... So these are 2 points here, which are the preimage of a point here, which was the image of a critical value, right? So you have a point over here, which is the image of a critical point. It has fewer preimages under f than its image will have under z goes to z to the d. And so we have to fix that up by taking maybe 2 of the preimages under z goes to z to the d and identifying them. And so what we can do is, we can do a kind of cut and paste. We kind of cut out the vertical slits starting at these analogues of this critical point. So these are quote unquote a critical point, meaning they both map to a value which came from a critical value over here. So they want to come from the same critical point here. So we cut it out along, we sort of cut a vertical slit along both of these things, and then we just glue the two sides together. So we cut and then glue. So we glue this side to that, and maybe the other side to the other side, and we get a new Riemann surface in which we have a single point mapping to the point here under z goes to z to the d in such a way that it pulls back to the critical value and the critical point mapping to that under f. Okay? So what we're doing is building a model for the action of f on the complement of its Julia set by starting with some map we understand extremely well, z goes to z to the d, acting on c minus the unit disk, and then we're just modifying this Riemann surface by cut and paste in a way which is compatible with the dynamics. Well, so if we do this cut and paste at this particular point, in order to get a map which is compatible with the dynamics, we have to look at the pre-images of these points, and we have to do cut and paste there as well. So this is a bit of a mess. So we do cut and paste at the critical points and their pre-images. Meaning, at each of these points in this C minus the unit disk, we cut out these vertical strips, we do a cut and paste there, and then we look at the pre-images under the map z goes to z to the d. We get a bunch of sort of also vertical strips, but lower down. We do cut and paste there, and we perpetuate this sort of backwards under the action of the dynamics. We do the minimal amount of cutting and pasting in such a way as to get a resulting Riemann surface on which z goes to z to the d still gives us a well-defined map on this Riemann surface. We've introduced critical points. We've introduced d minus 1 critical points, one for each critical point over here, at least counted with multiplicity. The resulting topological space we get is going to be, well, we started out with a cylinder. When we do this cut and paste, the net result is to kind of take a single circle and kind of pinch it off into a pair of circles. So let me sort of draw this over here. So let me back up very slightly. We get a picture of the following kind. So here's a picture of S1 here I'm going to think of as the boundary of the unit disk. And I can think of C minus the unit disk as sort of the outside of this. And so these vertical lines just become radial lines that were kind of on the outside, right? These radial lines that were kind of on the outside. This is the surface. This is this. So the outside of the unit disk, this is this Riemann surface. We have the map z goes to z to the d. And I'm going to do sort of cut and paste surgery on this Riemann surface compatible with the dynamics of z goes to z to the d. And the way I do it is, so these critical points, which I guess I was drawing in orange, if I had, say, a pair of critical points here, they each gave me this vertical line heading out to sort of negative infinity. I'm just drawing that as a straight radial curve here. And I do cut and paste. And when I do cut and paste, another way of sort of thinking about what actually happens when I do that is I can draw like a leaf sort of a lamination on the disk saying that, well, this thing here is going to be identified to this thing here. So I'm going to cut this open. I'm going to cut this open. And then having done that, let me sort of draw it like this. I cut this open, and I cut this open, and I kind of glue the sides together. The net result is to give me something kind of like this. Have I got that right? Yeah, something like that. So it's as though, topologically, I just took this line and sort of squashed it down. So topologically, it's the same effect as kind of tubing these two things together. Now, the one thing that's really, really important about the dynamics of F is it's occurring on a sphere, and the complement of the Julia set is therefore a planar surface, has no genus. So when we're doing this cut and paste and we're gluing things together, we had better get a surface of genus 0. Better not have handles. Well, the way to arrange that is precisely that the lines that we're doing this cut and paste along are not linked. So maybe there was another one over here, maybe some different critical point, and that gave me this. So these leaves are not linked, meaning they don't cross in the disk, and that means the effect of kind of squashing this one and squashing this one, it's still a planar surface. And then I have the pre-images of these guys, and they give me a bunch of sort of shorter things which are being kind of glued together like this. And so what we get in the end actually is this very nice dynamical system. We have a lamination of the circle, which is invariant under z goes to z to the d. And we also have kind of, each of these leaves has a sort of a height, a finite height, and the height of it gets multiplied by d, or log d, or, well, it depends what coordinates you use in the vertical direction. Yeah? So you get a kind of picture which is basically a lamination of the disk, which is invariant under z goes to z to the d, together with like there's some geometric data about how long the leaves are when they extend into the exterior. And so this thing here is a recipe we cut and paste, and the result is takes the exterior of the unit disk and produces a new Riemann surface. Right? Everything's being done in the world of Riemann surfaces here. So the new result is a new Riemann surface, which is topologically, we keep introducing sort of new holes, but never new genus every time we kind of go over one of these branches. So topologically, we've produced a Riemann surface, which is homeomorphic to the plane minus a Cantor set. And not just homeomorphic, I mean, see here, this is a parabolic puncture, right? So it's, we know conformally what this is. Together with the map z goes to z to the d, so I'm going to call this omega. So this is the result of cut and paste. Together with a map z goes to z to the d, this descends to give us some dynamics f from omega to itself. It's still degree d, because this is degree d, except now we've introduced some critical points, namely the biggest leaves here, and then the pre-critical points, the pre-images of those. So it now has, so it's still degree d, and d minus 1 critical points with multiplicity. And so it looks like it came from a polynomial. And so if you can fill in the complex structure over this Cantor set of n's in a way in which f extends holomorphically, well, you'll get a holomorphic map from the Riemann sphere to itself of degree d, which is to say it'll be a polynomial. I mean, it's fixing infinity, it'll be a polynomial. And the d minus 1 critical points are all in omega, and everything in omega is in the basin of infinity because it was in the basin of infinity here, and the dynamics is basically the same. So you will have produced something in the shift locus. So you can do this. It turns out basically this dynamics always extends over this Cantor set. There's a very simple proof of that. Maybe I'll just give it now. So the theorem, maybe call this realization theorem, and this was proved originally by Laura DeMarco and Kurt McMullen. They have a very different proof, but let me sort of say what this is basically that this Riemann surface omega together with f of this kind, meaning obtained by cut and paste from z goes to z to the d on the complement of this disk by a lamination, cutting and pasting along a lamination invariant under blah, blah, blah. You have to say what the conditions are, but this sort of model, this thing here arises from a unique polynomial in the shift locus. So this is equivalent to saying the dynamics of f on omega fills in holomorphically over the Cantor set of n's. So the proof of this, so there's kind of a very short proof actually. So here's a more or less equivalent statement. Supposing I have like a pair of pants, and maybe I have, instead of a pair of pants, I have like D holes instead of 2. It could be a pair of monkey pants, if you know that analogy. And I have kind of, you know, maps from the outer boundary to the inner boundary. Okay? In particular, I can take this thing and I can glue it inside itself, and I can keep gluing it inside itself, and so on and so forth. And the result is I'm building for myself a Riemann surface, which is topologically a disk minus a Cantor set, together with some dynamics on it, 2 self-maps which take it inside itself. The theorem is that this embeds in the disk in such a way that these maps here extend to holomorphic maps from the disk into itself. And the proof is, well, we just want to uniformize this. So we've got this pants together with this dynamics. So we uniformize the pants as a subset of the unit disk in any old way. And now I'm going to define a dynamical system on the space of, and maybe I have to fix an identification of the boundary with the boundary or whatever. I'm going to define it, or 3 points or something. I'm going to define a dynamical system on the space of ways of putting this pants inside this, which is as follows. Given this way of doing it, I take this disk and I glue this disk back in, and now I've got a new disk, and I uniformize this new disk. And I restrict this uniformization to the outside. And so that gives me a new map from the disk, from the pair of pants to the disk. So I'm defining a dynamical system on the space of maps of pairs of pants, well, inclusions of holomorphic injections of pairs of pants into the disk. So given the disk and ways of gluing the outside to the inside, given one map, I get a new map by just taking this disk, inserting it inside these 2 holes, and reuniformizing. And a fixed point for this map is an extension, is a holomorphic extension, because the map F on the Riemann surface here then just extends to this insertion map now on the disk. And so the proof that there's a fixed point is basically just, this is a map on a Teichmuller space, so it's distance contracting. There's a bounded orbit, so it has a fixed point. So those of you who are familiar with some theorems of Thurston in the context of Kleinian groups and rational maps, finding fixed points of the skinning map, that's a much more complicated context. This is a very elementary skinning map, but the reason there's a fixed point is the same. So anyway, so that's a kind of a cheap proof of this theorem, but it lets us understand the shift space in kind of now completely combinatorial terms. A polynomial in the shift locus gives us basically dynamics on this sort of infinite cylinder cut open and re-glued along a nice vertical lamination. So it turns out then that there's an extremely simple way to turn that information into algebraic geometry. And you can kind of see the braid groups arising as a kind of the first step in this approximation. So let me spend the remainder of the talk talking about that. Okay, so you've got F in the shift locus, gives you in a unique way this sort of cylinder, excuse me, together with some nice dynamics. And this cylinder has its sort of horizontal and vertical foliations. And the dynamics basically just moves things up one unit, right? This sort of came from just an honest cylinder. The dynamics here was just things move up by 1 unit, and they also kind of do a default covering in the circle direction. So the circle direction does whatever it does, and the dynamics here, again, just sort of moves things up 1 unit at a time. So here's how you get algebraic geometry from this. Let's choose some level, and then all the integer translates of that. And if I'm kind of lucky, I chose it at a level that happens not to have any critical points on it. So this is some level kind of, you know, k plus 1, k minus 1, k minus 2. I'm going to choose vertical coordinates for which the map just translates things up by 1 unit. And then there's a map, which I'm going to call the sausage map. And how do you make a sausage? You take a long sort of cylinder of meat and you keep tying it off at some places. So the result of applying the sausage map gives me a collection of Riemann surfaces, actually CP1s, whatever, something like this. Together with some dynamics, but the dynamics here just moves things up to the next level. And these guys have nice coordinates on them. They have a pair of foliations. They have the kind of foliation that does this. And then they had the vertical foliation, which sort of did this. And these maps preserve these foliations, or take each foliation to the pre-image by kind of like a branched map. So let's just cut it off at one level so that all the critical points are below that level. And maybe we cut it off at the first level at which there's some interesting critical points. So this is just the Riemann sphere, and these coordinates make it CP1. This thing is another CP1, and this map is given by a polynomial. And it's a polynomial with the property that it takes infinity to infinity, and it takes these points to whatever this point was, and this is the critical point. And then at each previous level, these points here are just the pre-image of these sort of marked points at the previous level. So this data is exactly the same as a tree of Riemann spheres, sometimes called a cactus, so it's a rooted tree. We have sort of infinity is a marked point in each of these Riemann spheres, and each guy is sort of attached to the next one at some bunch of points here, some marked points, and you've got the dynamics which just moves things up to the next level. And once I identify all these things with Riemann spheres, these maps are just given by polynomials. And this map has degree d, meaning the pre-image of each Riemann sphere, it's a finite set of Riemann spheres, and the sum of the degrees adds up to d. What's even better is we can normalize this by putting all these polynomials in Butcher normal form. And since the sum of the pre-images has degree d, below all the critical points, actually all the maps just have degree 1. And if you have a degree 1 map and you put it in Butcher form, it's just the map z goes to z. It's the identity map. So this entire picture is defined by a finite amount of data, the combinatorics of the tree and the finitely many polynomials of degree bigger than 1. And so the data describing this is a quasi-projective variety. And so you can recover this space by just looking at the space of these cactus maps, cactus polynomials, and taking it over all kind of combinatorial pictures. So there's infinitely many kind of combinatorial pictures. The difference between two critical points might be arbitrarily far. You might need, a lot of information to encode it, but it's always, for any particular guy, it's always a finite amount of polynomials. So this is sort of a description of this space in terms of algebraic geometry. At the very first level, you have the possibility that all the critical points happen to be in a single sausage. So the entire picture, so the special case is that there's a single guy which happens to have every critical point. So it has the d zeros and the d minus 1 critical points. So you just have a degree d map. So degree d map, which has d distinct zeros. And then below that, you have, I guess maybe it's going to be, below that you have d distinct zeros. And so the space of cactus maps, which is sort of as simple as possible, that all the critical points are in a single guy. So there's one polynomial of degree d, and everything else is the identity. This space is just the degree d polynomials with d distinct roots. Well, that's exactly the space whose fundamental group is the braid group of degree d. So that gives you a nice subset of SD, a nice sort of open subset, which is homeomorphic to the configuration space of d distinct points in the plane. And that's a subset whose fundamental group, it's a subgroup of pi1 of SD, is kind of a copy of the braid group. And so the entire fundamental group here is given in a kind of really interesting way as a sort of iterative perturbation of the standard braid group. I don't mean that in any technical sense, I just mean that it's refined constantly by, you kind of say, when things degenerate, you have kind of a new discriminant locus which tells you about the previous polynomial mapping where its roots have to go and so on. So you kind of look at the standard configuration space, look in complex dimension C d minus 1, you have this discriminant locus, and then at each point in the discriminant locus you're kind of blowing it up and putting over that a new guy, also of complex dimension d minus 1, or it's a total dimension d minus 1, which is sort of telling you about the discriminant locus of the polynomials at the next stage, and so on and so forth. So you kind of have this infinite tree repeatedly kind of blowing up the discriminant. You get a sequence of quasi-projective varieties, each one of complex dimension d minus 1, and each one of them describes a bigger and bigger subset of the shift locus. And I'm out of time, so I'm going to stop. All right.